Our team's primary design goal was minimizing the cost of the final product. A great product does not just have to work efficiently and properly, but it's also imperative that it is inexpensive. People need to be able to afford the product, not just know that it works. The aspect of the design that our team was trying to optimize was the flow rate. We optimized the flow rate by changing out the use of a cotton ball for the cheesecloth in order to close the opening. The cotton ball absorbed too much water that was put through the filter. The cheesecloth optimized the flow rate without letting media seep through. The housing unit was made up of a soda bottle inverted on itself. This was done to have the bottom half collect the filtered water while the top half housed the media. Cheesecloth was placed in the opening to stop the media from falling through while the water was filtered. This also allowed for maximum flow rate. 2 design iterations were completed throughout the process of building the filter. One iteration was the addition of aluminum oxide. This media was added to remove toxins from the water. The second iteration was swapping out the cotton ball for the cheesecloth. This would allow for maximum flow rate. We made 2 improvements to the photometer. At first, we used a red LED light. This proved to be less than optimal since the water being tested was red, meaning the red wavelength would not be absorbed. Thus, we swapped the red LED for a green one because green has the highest absorbency for the color red. We also added a styrofoam cup lined with black construction paper to block out the surrounding light. If we had more time, we would have liked to improve on the design by doing more iterations with various media. Then we would be able to determine the best options available for removing dye. On the left is a screenshot of the Arduino code we used for the photometer. On the right is a picture of the circuit diagram. In the circuit, the potentiometer controls the intensity of the LED, and the photocell varies its resistance depending upon how much light hits it. This is how the Arduino obtains its measurement. This is our calibration curve for the photometer. The plot consists of average absorbance versus concentration, and our graph shows a predominantly linear relationship. We created the curve by taking the dirty water, which we called 100% concentration, and finding the absorbance with the Arduino. We then diluted the concentration to 50%, 25%, and 12.5% and measured each of their absorbances. With these data points, we found the linear regression, which is useful for determining our filter's performance. According to the data shown above, our device performed very well. We first gathered the Arduino data for the clear water gathered from the sink. We then filtered the dirty water and calculated the absorbance based off of the photometer's reading. From the absorbance calculation, we used our calibration curve to determine the remaining amount of dye left in the water in comparison to the original dye amount. According to our data, our device filtered out 70% of the dye on average. The Arduino photometer was somewhat unreliable. This can be seen through the large variance in concentration percentages from trial to trial. This is the cost breakdown for our filter. The table contains a list of all the materials we purchased, the percentage of this material that we used in our final filter, and the cost of each material. From this, we found the net cost of our filter to be $104.75. To conclude, in this video we described how we optimized flow rate and filter cost, performed 2 iterations, and used a photometer to determine the performance of our filter. We enjoyed working on this project and getting to know our group members. Thanks for watching.